Going back to proving that there are exactly p minus 1 by 2 residues, you can basically think of it as pairing of the numbers. So you have 1 square, so this is again lagging, but yeah, you have 1 square is equal to minus 1 square, and 2 square is equal to minus 2 square, and so on up to p minus 1 by 2 into the point. And further, just as we showed, none of these values are really equal to one another. So 1 square cannot be equal to 2 square, and so on. Square contribute to minus 2 square, and so on up to p minus 1 by 2. So each of these will give a unique value, giving us p minus 1 by 2 unique values, which are actually quadratic residues on p, and the other p minus 1 by 2 values will be quadratic non-residues. So I'll just pause over here, and if you have any questions, please do mention. Right, Rishabh, so what I mentioned is that well, we have some value. In this case, this is just equal to 1, or rather congruent to 1. But so 1 square will be congruent to minus 1 square, will be some value here. 2 square, which is congruent to minus 2 square, will be some other value here. 3 square, which is congruent to minus 3 square, will be some other value here. 4 square, which is congruent to minus 3 square, will be some other value here. 5 square, which is congruent to minus 5 square, will be some other value here. 6 square, which is congruent to minus 5 square, will be some other value here. 7 square, which is congruent to minus 5 square, will be some other value here. 8 square, which is congruent to minus 5 square, will be some other value here. 9 square, which is congruent to minus 5 square, will be some other value here. 10 square, which is congruent to minus 5 square, will be some other value here. 11 square, which is congruent to minus 5 square, will be some other value here. 12 square, which is congruent to minus 5 square, will be some other value here. 13 square, which is congruent to minus 5 square, will be some other value a lot of echoes. Oh well, so you have this one pair here. Similarly, you have a pair of values here, and so on up to p minus 1 whole square, which is equal to exactly p plus 1 by 2 whole square. And you just do that note by at least if you consider the left hand side, let's say this value and this value, like both of those values are less than equal to p minus 1 by 2, and so if both of their squares are congruent mod p, then you can never have this solution. So from this contradiction, you basically get that there are p minus 1 by 2 different non-residues mod p, and hence there will also be p minus 1 by 2 non-residues. Right. Now, yeah, all the p minus 1 by 2 have to be different, because let's say two of these are similar. So let's say this square here, and let's say some I square here and j square here are the same. So I square congruent to j square mod p. Then we can just insert the values of I and j here, and we get that I has to be congruent to plus minus j mod p. But that is not possible because both I and j are less than p by 2. So I plus j cannot be p. And if I minus j is equal to p, then that just means I is equal to j, right? Yeah. So now that we have shown that there are exactly p minus 1 by 2 different values, a raised to p minus 1 by 2. Euler's criterion. Yes, this is binary. So, I mean, as part of the proof, we will see that this is equal to plus minus 1. But, I mean, just for your understanding, the first thing that should strike you is that when you set this, the square of this value has to be equal to 1. Yeah. So, now why is this true? Specifically, if we'll take two cases. Case 1, then it is a quadratic residue. That is Yeah, it will be congruent. So the way to look at this will be that right for A equal to B, actually, again, the reason why I'm not taking that is because the definition of Legendre symbol states that A and B are relatively prime, but for the specific case where A is equal to B, well, the solution would basically be that uh, would basically be multiples of B. So B is always a quadratic residue because all multiples of B squared will be congruent to 0 mod B. Exactly. So coming back to this, you have case 1 where A by B is actually equal to 1. This case, this means that there exists some x for which, well, we prove that there will exist exactly two different values less than p, for which x square is congruent to a mod b. So a raised to p minus 1 by 2 will be congruent to x raised to p minus 1, which for maths little states that this is equal to 1, congruent to 1 mod b. So in this subcase where A is a quadratic residue, it is easy to see that the value of A raised to p minus 1 by 2 is also equal to plus 1. Let's see what happens when A by p is minus 1. That is, A is not a quadratic residue. In this case, what we'll do is we'll use a nifty little trick here, in the sense that what this basically means is that for any value k, let's say, you have a pair of integers such that k prime is equal to a, k prime congruent to a mod. Right, and what this basically assures us is that k can never be equal to k prime. Right, so for all numbers from 1 to p minus 1, you can basically pair the numbers into pairs which are which when multiplied will give you a. Everyone with me so far? Yeah. So now what we'll do is we have a raised to p minus 1 by 2 is, and each A here can be divided into one pair. So if we can just substitute all of these p minus 1 by 2 pairs here with the values of a here, you'll directly see that a raised to p minus 1 by 2 is congruent to p minus 1 factorial. This is a little difficult to get, and if anybody has any doubts in this translation, please do mention. But once you get this translation, well, directly using Wilson's theorem, you have that this is congruent to minus 1 mod. Right. So we have two cases here. One is where A is a quadratic residue, and the other where A is not a quadratic residue. If A is a quadratic residue, then it's pretty direct in the sense that you have some value of x for which this is satisfied, and if you just plug that value of x back into a raised to p minus 1 by 2, then you get an x raised to p minus 1, which has to be congruent to 1 due to Fermat's little theorem. Again, we are relying on the fact that a and b have no are basically relatively prime, and hence x and p also have to be relatively prime. Right, going to the next condition where A is basically a non-residue, have for any k between 1 and p, you'll have some value of k dash. Actually, the value of k dash is just the k dash equal to, right. So I'll come there. K dash is equal to 1 by k into a. Actually, let me just, I'll repeat this with an example too. Where 1 by k here is the inverse of inverse of k mod p. Let's say we are talking congruent to 7, and we are looking at a equal to 3. Right. So we'll have 1 into 3 is equal to 3, or 2 into, that's the inverse of 2 is 4. So 3 4s are 12, which is 5. So 2 into 5 is 10, which is congruent to 3. 3 is already done. 4 into 6 4s are 24. Yeah. So these are the three numbers, which 3 pairs, which all multiply out to give 3. Right. you can see that for any value of a and b, similarly, you'll divide the numbers from 1 to p minus 1 into p minus 1 by 2 pairs. And then you'll substitute it here. So what you'll do is, instead of 3 raised to, let's say, 7 minus 1, 6 by 2, 3, you'll first open this up, 3 into 3 into 3, and each of these 3 here you'll replace with this one pair from here. So you'll have 1 into 2 into 5 into 4 into 6, which is just 6 factorial. Did you get that? Yeah. So that's how we basically move from here to here. Once you've reached the e minus 1 factorial, directly Wilson's theorem states that that is congruent to minus 1, 1. The reason this won't work for the quadratic residue is that you'll have cases where k is equal to k dash, and hence some numbers will be repeated, and hence this cannot be equal to p minus 1 factorial. Right, I was thinking of covering Gauss's lemma also, but maybe we should do that in the next class. We'll one more thing in that case. Let's see how to solve a random second degree equation in this space. So what I mean is that we have ax square plus bx plus c congruent to, let's say, k mod b, actually congruent to 0 because you already have the should I be able to see it now? Is this bit? Maybe this is bit. Right. So question is basically how we solve this, and the easiest way would be to piggyback on the quadratic equation. So those of you who remember, the quadratic equation can be arrived at by basically completing the squares, right? So how would we do that? We multiply, we first take the c to the other side. You have ax square plus bx congruent to minus c. That can be done. It's up to you either way. I mean, otherwise it will be in terms of a till the end. That's all. And since a inverse is really a part of the value within this, not really a part of the discriminant. Basically, I'm first trying to reach there. So yeah, you can just remove the a by multiplying with a inverse, or what you can basically do is that basically becomes a much more simplified method because you won't have to keep taking care of the a's, but otherwise you can just multiply this whole thing. Sure, let's do it that way actually. plus dx by a. Right. Have this. Now, what this would basically be is we can x squared plus e by ax plus b square by 4a square. Yeah. Square by 3 square equal to minus c by a plus b square by a square. That will basically be equal to x plus e by a square so if b square minus 4ac is a non-residue, then you really don't have any solution to this square. Otherwise, you can find a solution. So if you don't cancel a's out, actually it becomes much clearer in a way, because you get the b square minus 4ac term directly. You get ax plus c whole square. You can just multiply the above with a square on both the sides. Get ax plus b whole square is equal to b square minus 4ac. So if it is a residue, then you find the two values which ax you can equate, and then just divide this into two parts. So I guess that's all for today's class. We'll pick up from Gauss's lemma onwards in the next class. If anybody has any questions about this, then please do ask. Yeah, all division here was modular inverses. And as we mentioned, the value of, alright, I should have basically mentioned that A is a relatively prime to B, but otherwise you basically have this term out and then Bx congruent minus 0. Then I thought it was till 7. In that case, we have time to cover Gauss's lemma. If everybody is free, then we can just check. Just give me a minute, please. Alright, so then we can actually cover Gauss's lemma too if everyone's free. Yeah, and as Ashir mentions, this will be unsolvable if b square minus 4ac is not a residue, right? It will not have any solutions at all. In that case, let's just cover Gauss's lemma. Gauss basically states that n equals to number of that's what I had understood. That we have only one out classes from now. Because as far as I know, there are some other classes planned in the future from 7 o'clock onwards. But if nobody really has any class now, we can just extend this for half an hour. Yeah, it should be definitely over before 8. Yep. Ashir, as you mentioned, this is basically you take a look at all the numbers from here and you reduce these into its lowest positive values congruent to b, some values congruent to b. Some values more. And then you look at the question, look at the number of such numbers which are greater than b by 2 and equal to number of these numbers which are greater than b by 2. Please note that I have mentioned that we have to reduce this to the small positive numbers, so we cannot just reduce these to b plus 1, b plus 2 and then say that everything is greater than b by 2. have A by B on minus 1 raised to n. So is minus 1 raised to this actually has a pretty interesting proof, but let's first write these out into sets here. Let's call set L and M. L are all those values which are, let's say, greater than p by 2, and M contain all of those values which are less than p by 2. Sorry, less than 2. Right, so we have just distributed these residues into two sets. Actually, since they're sets, let me write them as capital N, L and capital N. Depending on whether they are larger than or smaller than p by 2. Right? I'm trying to prove this. So basically, we have all of these numbers here, a, 2a, 3a up to p minus 1 by 2a. And the lemma basically states that if you first reduce this to its smallest positive values, mod p, and then you count the number of these numbers which are greater than p by 2, and name that as n, then the value a by b, the Legendre symbol here, is equal to minus 1 raised to n. So if there are an odd number of such numbers, then a by b is negative 1, and if there are an even number of such numbers, then a by b is positive 1. Right. So the way we are approaching this is we'll first divide all of these residues into two classes, capital L and capital M, where capital L is the set of all residues greater than p by 2, and capital M is the set of all residues less than p by 2. It can never be equal to p by 2 because p is a non-prime. Right. Now, what we do is no two numbers within L, let's say L1 and L2, cannot be equal to each other. Can you tell me why that is true? So, L is basically the set of all of these residues which are greater than p by 2, and I just stated that no two let's say both 2a and 3a, for example, can be written as some values greater than p by 2. So let's say 2a is congruent to L1 and 3a is congruent to L2. In fact, let's just look at all the values here. Let's say 2a is or I a is congruent to xi, and j is congruent to xj, then xi is not congruent to xj. Can you just be, yeah, exactly. So IA is congruent to XI, so you can just write this as IA and IJ. By contradiction, if these are congruent, then, sorry, AJ, if by contradiction these are actually congruent, then we can contain A surf and we can say I is congruent. So hence Li is not equal to Lj, Mi is not equal to Mj for any values here. The next thing that I prove is that P minus Li is congruent to Lj. Sometimes can you
two are smaller than P by 2. So Li is just some element of this set, and Mj is just some element of this set. Exactly. So let's assume otherwise that P minus Li is congruent to Mj. That means P is congruent to A times some two numbers with the additional constraint that I and j are both between 1 and P minus 1 by 2. Correct? Because Li is congruent to A times something and Mi is congruent to A times something else, with both the numbers lying between 1 and P minus 1 by 2. Yeah, P cannot divide I plus j because I plus j will be less than P minus 1. Hence, hence P minus Li can never be congruent to Mj. Right? Yeah. Our basic assumption here is that given that we are writing this Legendre symbol, is that the GCD between A and P is 1. Ij will in fact be less than P minus 1 by 2 because that's the number I have mentioned here. So I plus j will be less than P minus 1 and hence right. So now what we have here is for all the numbers within L, I'll take the values P minus Li, and for all the numbers within M, we'll take simply the value Mi. Right. Now, here's the idea. We'll show that this set here of all of these numbers is equal to the set of numbers from 1 to p minus 1 by 2. Now, the reason why this is true is basically, as I mentioned, each of these have to be separate values. So none of the p minus li can be equal to each other, none of the mi can be equal to each other, and there can not be a no, there are actually only p minus 1 by 2 terms, right? Because I'm dividing all of these into these two sets here. So the sum of all elements in L plus the sum of all elements in M is actually equal to p minus 1 by 2. Right. So each of them mod p is basically different, and by how we defined these numbers, each of these are less than equal to p minus 1 by 2, because if any of these numbers is greater than p by 2, then it would lie in L, and we are taking p minus li and mi, both of which are less than p by 2. So they're different and they occupy this space, and the total cardinality is equal to this, and hence this equation is true. Is everyone okay with this equation? Because we'll be using this. Right. So now what is left to do is just basically multiply all of these numbers. So p minus li times mi, of course, taking the product overall mj overall ij will be equal to p minus 1 by 2 factorial, right? And then we can write p minus li just as minus li to further write this as minus 1 raised to mod capital L into li into mj. Right. So, Mayuk, did you understand the equivalence between these two sets? Right. So, what I'm doing here is, since all of these numbers have been divided into two sets, capital capital L and capital M, depending on whether they are greater than p by 2 and less than p by 2. Further, we prove that there are no elements in L and M such that p minus the element in L is equal to the element in M. So, for example, if one lies in M, then p minus 1 cannot lie in L. Right? And that was simply because if this is true, then you can write P as congruent to Li plus Mj, and then we can just write those numbers back in terms of A. Yeah, if one lies in M, then P minus 1 cannot lie in L. So in which case you get this congruence, P is congruent to A I plus J, and P, since both I and J are, lie between 1 and P minus 1 by 2, this cannot really be true, right? So now we just take the set of these numbers. So for all elements in capital L, we take P minus that element, and all elements in capital M, we just take as it is. So the size of this set is P minus 1 by 2, right? And we have proved that they are all distinct elements and they are all actually smaller than P by 2. So this set basically is supposed to be equal to this set, right? Now I'm just multiplying this out. So I just multiply each element in this set and multiply each element in this set to reach here. Now what I do is minus 1 raised to the number of elements in L. Sorry, I'll just write this. Yeah, minus 1 raised to the number of elements in L into Li into Mj is equal to P minus 1 by 2, is congruent to actually P minus 1 by 2 factorial. Congruent to right, and then we just put back the values of Li and Mj. So Li into Mj is basically equal to A raised to P minus 1 by 2 into P minus 1 by 2 factorial. Because that was how we defined it by this congruence here. Minus 1 is raised to the size of the uh, basically, yeah, the size of the set L, right? Because that many times the negative term will come. So in fact, going on forward, let's just term the cardinality of set L as equal to small n. So minus 1 raised to n times A raised to P minus 1 by 2 times P minus 1 by 2 factorial is congruent to P minus 1 by 2 factorial, right? Are you fine till here? Now we can just cancel these out because these are both relatively prime to P. And we basically get that if A raised to P minus 1 by 2 is congruent to 1, then so is minus 1 raised to n. And if A raised to P minus 1 by 2 is congruent to minus 1, then so is minus 1 raised to n. So basically, from here using Euler's criterion, we can write that A by P is equal to minus 1 raised to. Right. Mayuk, so just tell me where you're stuck. I'll label this 1, this 2, and this 3. So are you stuck in reaching equation number 1 itself, or the movement from equation 1 to equation 2, or how we move from equation 2 to equation 3? From equation 1 to equation 2, this n is just labeling. We have labeled the size of the set L as small n. Then what we did is we just looked at what L's and M's were. So when we multiply all the L's together and all the M's together, it is just congruent to multiplying all of these numbers together, right? So that is equal to a raised to p minus 1 by 2 into p minus 1 by 2 factorial. Why? Because there are p minus 1 by 2 a's here, and then all the numbers in front of the a multiply to give a p minus 1 by 2 factorial. So li, like the multiplication of all the li's and all the mj's together, gives us this value here. This is just substitution of our original value, right? So we just reach there from this. So if we look at all the terms in L and all the terms in M together, it's just all the terms here. And so I can just substitute these values back. And when I substitute these values back, since I'm multiplying everything together, I have a raised to p minus 1 by 2 into p minus 1 by 2 factorial. So we can just substitute that here, and then these two p minus 1 by 2 factorials can be cancelled out to get minus 1 raised to n into a raised to p minus 1 by 2 congruent to 1, which means, well, the this value can take either plus 1 or minus 1 only. So when this is plus 1, this is also plus 1. When this is minus 1, this is also minus 1. And since this value is equal to this value by Euler's criterion, hence this also has to be equal to this. Is it clear? Yeah. So I guess we'll stop over here. Next class, we'll actually look at reciprocity. Basically, we will look at what happens when we bring two primes into consideration. What is, let's say, 3 by 7 into 7 by 3 and so on. This is the end of today's lecture. You can log out. Good night, everyone.